In this brief video, we're going to go over some of the basics of cell disruption via homogenization, which is commonly used after you've collected your cells into a cell slurry after the fermentation to break the cells open and recover the protein that's inside the cells. So homogenization basically acts to break up the cells by forcing the cells through a very small orifice at very high pressure. So you have a pressure valve that you screw against a seat and an impact ring that surrounds this, and you force the feed through. It's a very tiny opening at high pressure, and via a combination of shear, cavitation, impact, and pressure shock, you basically bust the cells open, causing release of the intracellular protein. We can model or estimate the percent of the protein that's released. So the R would be the recovered protein, or the protein that's released, as a function of the maximum potential recoverable protein. And the key variables that drive this release rate would be the number of passes, so how many times you go through the homogenization, and the pressure at the homogenizer. These other constants, K, beta, and alpha, are a function of the configuration for the different type of homogenizers, as well as the types of cells that you may be homogenizing. So this would be an example of the amount of protein released as a function of the number of passes through a homogenizer. Remember, there's the more passes, the more release you have. And then increasing the pressure also increases the protein that's released. For E. coli, we can rearrange this equation to give us a term D. So D is the fractional release of protein, which is R over R max. And these constants can be used to estimate the level of release for E. coli, right? So it's a function of the cell concentration, which makes sense, the number of passes to experimentally determined coefficient, and the pressure to an experimentally determined coefficient. These would be some cost estimates and size flow rates for a different homogenizers. So they would cost anywhere from 50,000 to over $1 million, depending on the flow rate you need and the pressure you need to operate in. From the previous equations, you could figure out how many passes you would need at a given pressure to get a certain type of release, and then you could dictate the amount of flow that you would need. So if you haven't reviewed the lecture on how to design a centrifuge, the design for the homogenizer would be very similar. You have to figure out what your flow requirements would be, meaning how much volume you want to put through your homogenizer, what pressure you need, and how many passes you need to get the lysis that you want, and that would dictate what kind of model that you would want to buy, and the cost as well as the operation. Now again, if you remember our summary metrics for downstream recovery, we have three. Delta, which is the concentration factor, which is the product at the end of the step over the product concentration before the step. The alpha separation factor, which is the product to contaminant ratio at the end of the step over the product to contaminant ratio before the step, and then the percent yield, which is the total amount that you receive at the end versus the amount that goes in. For homogenization, we can estimate these coefficients pretty easily. So percent yield would be the amount of protein that's released over the potential maximum amount of protein, which makes sense. Delta in this case is actually equal to the percent yield because you're not actually concentrating or changing the volume at all. You're just busting open the cells, so that would make sense. If you have debris that comes out that's not soluble, which would be the protein that's not released, it's lost, and so that would impact your yield as well as your concentration factor. And then alpha is equal to delta when considering the non-specific release of contaminants, meaning homogenization really does not achieve any separation